these dates around if anybody wants a second hit. I'm your pusher today. The first one's free. The next one you're going to have to pay for, right? Huh? Very good. Well done. All right. So homework 9 is due on Thursday, and this is going to be one of those really quick turnaround assignments that we're just introducing the concepts today. But luckily there's only 4 problems and they're pretty straightforward. Like I just graded homework 7 today, and so you can see my comments for that. You know, I think the problems on homework 7 were pretty easy. You know, like I saw some people solving the entire assignment on a single page. This may be another one of those. Let's talk about the design project phase 1, but just as a reminder, for phase 2, you're going to need to upload 2 maps for that, and I'll show you a picture of what one of the maps ought to look like. All right, so about demand estimation. I'm going to be going over your demand estimation submissions. I've already done a few of them, but the majority I still need to do. And I'm just going to very briefly tell you if I think something is high or low. I have a range of typical values that I'd expect given the conditions that I assigned to you. And if you're within that range, I just won't comment on, let's say, the north loop or the south loop. But if you're kind of outside of the range of what I'd consider normal, I'm going to flag that in the comments. And that doesn't necessarily mean that you're wrong. It may just mean that you're assuming something differently than I assumed, and that's fine. What I'd suggest is just review what you assumed and see, you know, like do a reasonableness check or double check your calculations, and if you still feel good about it, then that's fine. I'm not saying that you have to change, and if you want to come and check with me in my office, I'm happy to talk to you about it. I don't want to say what I'm expecting your flow rates to be. That would kind of defeat the purpose of asking you to generate demand estimation. But if you feel good about your calculations, then just be sure that you explain, particularly in the final submission. If I said that your north network was too high, then maybe in the description of the report explain the details so that I understand why your assumptions are beyond what I was expecting. The best thing you can do is just kind of on your own identify the errors and correct them, and that's what the final submission should be, is not only just submitting what you submitted before, but explaining how this process was optimized and like what assumptions changed from the first submission to the second. But it's not just the amount of water that's important, and it's the timing of it too. And using it as an example, I had one of the factories where I told you it's a certain number of million gallons per week, right? Was that the food processing plant? All right. So if you assume that the food processing plant is open 24 hours a day, 7 days a week, then that amount of water is going to be spread over a high number of working hours. And so that would bring the design flow rate low. But if you sized the pipe going out to that food processing plant with that assumption, the pipe would be smaller than if, say, they are going to be working only 40 hours a week. Because if they're only working 40 hours a week, then that same amount of water has to get through the pipe in a fewer number of hours. And so the pipe would need to be larger. And so pay special attention to what the assumptions behind the watering of the lawn for the golf course. You know, they're not going to be watering 24 hours a day, 7 days a week. The timing of the factories, the food processing plant, you know, how water's used at the sports stadium. They don't have the normal peaking factors at the sports stadium that there might be in a residential area. So pay special attention to that. I hope to have the individualized comments finished so that you'll have those by the end of the week. But it seems like these days the whole universe is conspiring to get me to spend my time in ways that isn't related to my actual job. You know, we're interviewing a lot of people right now at Marshall. You may have seen them around trying to hire new faculty members, and anytime one of them comes to campus, it's just, it's murder on the things I want to be doing, which is looking at your demand estimation stuff. So I'm going to do that as quick as I can, but I regret it hasn't already been finished. All right, phase 1 of the project we've submitted your draft for is basically answering the question, how much water is going to be used in this hypothetical development. Phase 2 could be summarized very briefly as saying, how big should the pipes be? And it's an optimization process. It's not something that you're going to be able to just once apply a size and it will be the right size the first time. By optimize, what I mean is, remember there's a band of acceptable pressures. The minimum pressure should be 240 and the maximum should be 850. How do you pressurize the water in the network? What's causing that water to be pressurized? Elevation head of what? You're right. There's a reservoir up on the hill. So if you put the reservoir kind of low on the hill, there's not going to be much pressure in the network. But what if you put the reservoir too high on the hill? Well, at night, when people aren't using very much water, there's a static head. Basically, when the flow rates are zero, the pressure at each point is just defined by the hydrostatic equation. So if your reservoir is all the way up by the spring, for example, then your pressure at night, when nobody's using water, would exceed this maximum. So what you're going to have to do is you're going to be juggling having the reservoir nice and high on the hill and making the pipes as small as possible, because the smaller the pipe, you're saving money. But if the pipe is too small, then during the daytime hours when people are demanding a lot of water, the pressure could go below 240. So what makes it an optimization is you're just making the pipes barely large enough to be within that design criteria of 240 to 850. And the 240, the low end, is what you're going to see when you have your peak condition. And then the high end is going to be when there's no flow rate, no demands at any of the junctions. And that's why I ask you to prepare 2 maps for the next phase of the project. By the way, if you don't feel comfortable with water gems and you want to just have a basics introduction, I've pasted each of these links into MU Online in the project folder so that you can watch these YouTube videos where I'm explaining how to draw network elements, how to get in and edit the flex tables, and also if you don't have a tool for creating PDF files, then there's an open source PDF printer that you could use, and there's a link for that as well. But let's take a look at this map. This is a student submission from a couple of years ago, and this student did a really nice job. All of the annotation is clear and easy to read. None of the annotation is on top of any of the network symbols. It's large enough that you can see it relative to the size of the symbols, and it has all of the things that need to be identified. So when I look at your map, I should see where are the pipes, their diameter, their length, and what flow rate is going through them. Now back in these days, I told the students where the pipes had to go, and that's why they have these enclosed loops. And if you've already started to think about where your pipes are going to go, you can save money by eliminating some of these network elements. Like the pipe GF, it doesn't necessarily need to be there, right? The water could go to G from here, and it could go to F from the direction of E. So don't look at this map and say that in your own mind that you have to have pipes in all of the locations that are shown here. What I'm showing you this map for is just to show you an example of nice looking annotation. And so those are the things that should be annotated. And this map that we're looking at, you can see is at the high flow design condition. And so the lowest pressure here, it seems like, is on this side of town. The pressure is down to 275. Here's 274. So they're getting pretty close to the lower limit. And there would need to be another map where you'd go into each of these junctions where there's flow demand and you'd reassign it to 0. And then you'd execute the model again. It would update the pressure annotations, and so that we could see what are the pressures when there's no flow rate going through it to make sure it's not above the upper limit. So are there any questions? Yeah, go ahead.
Is there a way in water gems to set it up in like a layer of sort where you wouldn't have to go on and change it to 0?
Mm-hmm.
Is there a way to do that? Is that beyond the scope of this project?
Yeah, so like creating design alternatives, right. I think that there is. The easiest way to do it, I think, is to create a network and then just do a save as, and then separate files. But if you're in the flex tables, you can also global edit so that all of the flow rates that you've put at the junctions, you could global edit it down to 0. But that part could be potentially a little tedious. Yeah. Go ahead.
Take one of the pipes out, optimization, is it still considered a loop, or is it calculated a loop?
No, it's not a loop once, so for example, if we took out this pipe GF, then it's no longer a loop, but WaterGems can still do the calculations. It can still just use the nodal method for anything that's not an enclosed loop. But it takes away the ambiguity for that entire leg of the flow of where the water's coming from. It doesn't no longer have two options. So if anything, it makes it quicker to converge when you remove those pipes. All right. So that's what's up next. And if I'm not mistaken, that submission is due a week from today. Is that right? All right. So a week from today is when those draft maps are due. And you can begin laying out the location of the pipes even before you hear back from me on the demand estimation. But it's actually, you'll find that once you get good at WaterGems, it's really easy to make changes, and you'll find a pressure's too low in one spot. Let's say, what if this junction at G was saying 200 kilopascals? Well, then your move when the pressure's too low is to increase pipe diameter for one of the pipes that's feeding water to it. So you can see here the water feeding G is coming from O. So if my pressure was too low at G, then I just change that from 150 to whatever the next pipe size increment is. And I think maybe it's 175 or 200. I give you the increments on the handout. And when the pressure is too high, then maybe you could reduce the diameter a little bit. So here, for example, we see that at junction L, the pressure is 331. So that's above the limit. So maybe we could try and jump down this pipe AL. But if we do that, all of the nodes downstream of that are going to be affected too. So it becomes kind of a balancing act. Like, are you better off financially making this big pipe a little bit smaller, and then having to increase some of the downstream pipe sizes? It's like kind of an interesting optimization. Now, there's a tool inside of WaterGems called Darwin Designer. And in Darwin Designer, you can tell it how much each pipe costs, and it'll automatically do your design for you. It will do hundreds of different iterations, and it'll find the one that produces the lowest cost. I've had students in the past who've gone to the trouble of figuring out Darwin Designer, and it's not brain surgery, but I'm not going to show you how to do it. And if you like to do it, then that's great. I think I may have a demo on YouTube where students are showing how to use Darwin Designer if you want to search for it. Go ahead.
I don't see it on there. Would you have to mess around with the pipe material? It's not, I don't see it listed, but I didn't know if you were given.
No, you should assume, in the handout, I don't know if it says ductile iron, but material isn't something you'll be optimizing. That's a great question. Maybe in the future I'll have plastic options or something like that. Yes?
Also for elevation, would be a good idea to require a slide on each node to have elevation.
Yes. Yeah. Oh, no. It doesn't have to be annotated, but you are going to have to put the elevation of each junction into WaterGems for it to know what the pressure is going to be. I'm glad you asked that, because that's an important thing, is that you have to put in the elevation of the reservoir, elevation of each junction, because without that, it's not going to know the pressure. Yeah, but a couple of things about that is when you move the reservoir location, you're going to have to update the pipe length. The higher on the hill you put the reservoir, that's going to increase the pipe length. If you take the reservoir too high, then the risk is that the pressures will be too high in the static condition. And if the reservoir is too low, then it's kind of like you're leaving money on the table, because the higher the reservoir is on the hill, it's kind of like free money, because that's what allows you to make the pipe sizes smaller. If we move this reservoir down to 250, then I'd have to increase all these pipe diameters to make the minimum pressures that are required. The reservoir elevation is kind of like the fuel that pressurizes the system. It's where the energy is coming from. All right. Let's talk about open channel flow. Specific energy. Now, we've touched on this in the previous recorded lectures. I struggle to even remember what's in those lectures because I recorded them in early February. So it feels like a lifetime ago, but I'm pretty sure that we talked about energy per unit weight of fluid. And so, this is just kind of how the energy equation is different for closed conduit flow compared to open channel flow, where instead of the pressure head, remember that when we were comparing the two, we said that there is pressure head, elevation head, and velocity head in closed conduit flow. And the way that changes is that we have depth and elevation and velocity head. Okay, now specific energy is saying let's take the bottom of the channel as our elevation datum. And so now we're not even going to worry about the Z term anymore. Specific, the word specific just means relative to the channel itself. And so how much energy is there above the bottom of the channel? The only two terms that are remaining are the depth and the velocity head. And one of the substitutions we've made in the past, instead of velocity, sometimes it's more convenient for us to express it in terms of flow rate Q per cross-sectional area. And the reason why is we don't exactly know what the velocity will be, but in some cases we do know the flow rate. And we're solving for the depth y. And so if you're solving for y, then y would be here in the first term, and then y would also be one of the factors that goes into the cross-sectional area. You'll see that a little bit later. Okay, so now take a rectangular channel as an example. We want to put 10 cubic meters per second through this channel. It's 4 meters wide at the bottom and at the top because it's rectangular. Both lowercase and capital B are 4. And so how many different combinations of velocity and depth could there be? It's an infinite number, because we could have like a really shallow depth and the water moving at a high velocity, or it could be that the velocity is very slow and then it would have to have a very deep depth to convey that same 10 cubic meters per second. So we could create kind of like a hypothetical table, and this isn't all of the values. There are many more besides this, but this is just to make the point that for a certain channel, if we want to put 10 cubic meters per second through that channel, there's the end of the range where we've got a high velocity, and it's going to correspond to a lower depth when we go through and do the calculations. And then there's also a low velocity, like the slow-moving water, that's going to have to be deeper to satisfy continuity. Okay, so in this table, the cross-sectional area can be calculated just as Q divided by V. So if we do that calculation, then we'd have to have a cross-sectional area of 1 square meter in order to get the velocity of 10 meters per second. And then down here on the low end of the spectrum, obviously it's going to be the cross-sectional area is 10 square meters in order to get the same velocity. So that's how we would calculate the area column. The depth column, because it's a rectangular channel with the bottom width of 4, then the depth is just going to be the area divided by 4, because area is B times Y. So we already know B and A, and so in essence we're just saying area divided by B, and in this case the B was 4. Now, there's a reason why we're doing this, and it's because what we really are interested in is the specific energy. And so using this formula for specific energy, we can find the specific energy for all of these different depths. Since we're a little bit pressed on time, I normally would have you calculate each of these just to get practice using the formulas. But because of the quiz taking up a little bit of time, we'll just skip over that and take a look at the entire data table. The specific energy is pretty high when you've got a high velocity, because if you look at the specific energy, it's got two terms here. And when you've got a big velocity, then that's going to make the velocity head term big. If you have a really large depth here at the lower end of the velocity, you can see now our depth would have to be 2.5 meters in order to achieve a flow rate of 10 cubic meters per second at such a slow velocity. And so, again, we've got a big specific energy because the depth is so large. But you'll notice there is a minimum point here. And it's not coincidental that I put in this velocity of 2.905. I put that in because I knew it was going to be the velocity and depth combination that gave us the lowest specific energy. This makes the most sense when we look at a graphical representation of it. So let's do that. Let's graph a couple of things. First of all, this is just a graph of depth versus velocity. So remember, this is all for the same flow rate through the same channel. This is for Q equals 10 cubic meters per second through that rectangular channel that has a bottom width of 4 meters. So here's our channel, B equals 4, and this is for Q equals 10 cubic meters per second. So what this first figure is showing is you can either have a high depth and low velocity, or you can have a high velocity and a low depth. There's this infinite number of combinations of depth and velocity that give you the same Q of 10 cubic meters per second. So this isn't as important as the next graph. The next graph is going to be a graph of specific energy. And so going back to this table, I want to graph the specific energy as a function of flow depth. So remember that there was a minimum point. And here is that minimum point. And this figure is really important. You're going to be making figures like this in Excel in order to identify some things. And so let's pick it apart and see what's so important about this figure of specific energy versus flow depth. It's saying that there's this minimum point where we had the lowest specific energy for a certain flow rate. And that corresponds to something we call the critical depth. And you remember that you calculated the Froude number for the assignment that you turned in recently where you were classifying the flow regime. And the Froude number tells you if the flow is subcritical or supercritical. Well, that's what this is related to, where we're saying the critical depth, we're saying there's a certain depth that the water can go through the channel, and the least amount of energy possible is when the water is flowing at that critical depth. And if we're looking for hydraulic efficiency, then the most efficient way to convey flow, a certain 10 cubic meters per second for the lowest amount of energy, is at the critical depth. Now, why are there so many different combinations of depth and velocity? It's because there's an infinite number of slopes that a channel could be at. If you pour 10 cubic meters per second down a really steep slope, then it's going to be shallow because the water is going to be picking up a lot of velocity. But if the slope is relatively mild and shallow, like the Ohio River has a very shallow slope, then the depth is much larger because it's moving more slowly. So there are a lot of factors that play into that, including the roughness of the material, the geometry of the channel, and so on. But slope is the main factor that we can change and see this many different varieties of flow depth and velocity. So I want to pause for a moment and see if there are any questions so far. Go ahead. Use what? When flow is scouring something? No, the main equation that we'd use for that is the shear stress equation, and we'd then need to compare it to the cohesive strength of the material that the water is flowing over. So this isn't really so much related to scour, but it is true that when you have a really high flow velocity that you're going to see more scour than compared to a lower flow velocity. The region below this critical depth, any depth less than that is a supercritical depth because the water's moving fast. Any depth above the critical depth is a subcritical depth because it corresponds to a lower velocity. So here's what I was just saying. The minimum specific energy corresponds to the critical depth, and when your flow depth is larger than that, conditions are subcritical. And it's a little bit confusing for students, I've found, to have the flow depth greater than the critical depth super. They sometimes accidentally flip the sub and the super because of these signs. And so I put a little note in parentheses there to try and help you keep it straight, that subcritical flow is because the water velocity is slow, and you'd have to have slow moving velocity if you've got it really deep. So think that the deep water is going to be because you have a shallow slope, and so the water's not moving very quickly when you have a shallow slope. But when you have a steep slope, like remember that spillway in California? It's a very steep slope. Conditions on that spillway are supercritical. And so the depth of flow on that spillway would be less than the critical depth, fast velocity. You can also talk about the top channel width because for a trapezoidal channel, the top channel is the width of the channel is going to be changing. Now it won't be changing in a rectangular channel. You know, if you have critical flow or subcritical or supercritical, the top width is always going to be 4 in this example of the rectangular channel. But here if you have a trapezoidal channel, then the top width is going to be changing. It will be very large for subcritical flow. It will be smaller for supercritical flow. But then when you have the critical depth, then what we'd say is that you have the top width, capital B, is a subscript C there, critical top width. Yeah. Yeah, sometimes, was there somewhere earlier that I had the capital T in the notes? Yeah. Yeah, the book changed the notation, so I've tried to update the slides with the capital B. But yes, T equals B. Capital T is, it means top width. Thanks for asking that. And so here's one of the formulas where previously it had the capital T instead of the B. This is the formula for the Froude number. And here in the first term, it has this D there, and that means hydraulic depth, which is the cross-sectional area of the channel divided by the top width, capital B. We're going to talk more about the Froude number and how to calculate it throughout today. But Froude number of less than 1 means conditions are subcritical, and Froude number of more than 1 means that the flow conditions are supercritical. And so you can substitute in your depth of flow into the formula for cross-sectional area, and if you know the flow rate and the corresponding top width B, you can put all of those flow conditions into this equation and find the Froude number. And if it's less than 1, that's subcritical. More than 1, it's supercritical. Or you could say, what is the critical depth? You could say, at the critical depth, the Froude number is equal to 1. Substitute 1 into Froude, and you could solve for y. You know, y could be an unknown. And then you'd solve for the critical depth. Okay, now more about this hydraulic depth parameter, D. If we have some trapezoidal channel, for example, then the hydraulic depth here is just going to be the cross-sectional area divided by the top width. Now, of a rectangular channel, think about the top width is the same as the bottom width. And so for a rectangular channel, the hydraulic depth is going to be the area, which is B times Y, divided by the top width, which is just B. And so for a rectangular channel, the hydraulic depth is equal to just the flow depth. And the reason why that's sometimes significant is because you may have a rectangular channel, but also for channels that are very wide, like rivers that are shallow and wide, then they behave as though they're rectangular channels. So say, for example, we had this channel that is relatively shallow, and its width is very large, meaning like 20 times more than the flow depth. So if the width is more than 20 times the flow depth, then you don't have any air approximating this irregularly shaped channel as a rectangular channel. And the reason why is because these edge pieces are relatively small for a really wide channel. And so when you get beyond a ratio of about 20 to 1, then you can make that approximation. And the very wide channel approximation is something that we'll use a lot later on when we're trying to calculate flow depths upstream. But just be aware of that very wide assumption, and what it allows you to do is it allows you to say that the hydraulic depth is equal to the flow depth, Y. All right, so back to the same figure from before. Remember, the same figure from before, our critical depth was 0.866. When we had the table, I think we found that Y sub C was 0.866 meters. All right, so if you have the flow of 10 cubic meters per second and the depth is 0.25, is that supercritical or subcritical conditions? Super or sub? So when you have here this minimum and a specific energy point, and now we're saying, what about for the depth of 0.25? So what if Y is less than YC? So is it super or sub? It's super. That's right. Supercritical. And we could validate that by actually calculating the Froude number. We put in the flow rate of 10 cubic meters per second, square it, times the top width of 4 meters, G, and the cross-sectional area. Cross-sectional area is 1 because it's the 0.25 depth times the 4 width. And so the Froude number is greater than 1. And so that is another way of confirming that the flow conditions are supercritical. Now, for the deep depth of 1.25 meters, so above that minimum specific energy point, the conditions are going to be subcritical. And we can either do that just by comparing the depths and knowing that anytime the depth is greater than the critical depth, that means conditions are subcritical. Or we could calculate the Froude number. And then that's another way of classifying the flow regime. Any questions about that? All right, so an alternate depth. An alternate depth is defined as a depth that has the same amount of specific energy, but is different from the depth you're at now. So imagine drawing a vertical line through the specific energy curve. There are two different depths that have the same amount of specific energy. So you could have, for example, the water moving at a high velocity and small depth, and that could have the same amount of specific energy as a different flow conditions that had a larger depth but low velocity. So here's our curve. That's that same rectangular channel that's carrying 10 cubic meters per second. What is the specific energy when the depth is 0.5 meters? I'd like you to calculate that. This is an important example, so we'll take the time to actually do this one. Find the specific energy when we've got a depth of 0.5, and then what you can do once you solve for E is then find the other depth that also has that same amount of specific energy. And so you'll be substituting in the first part, calculate E. So let me summarize that here on the board. Step 1, calculate E for the depth equals to 0.5 meters. All right. Step 2, for the same E, find the alternate depth. All right, so what that means is that you're going to have E equals y plus q squared divided by 2g, and now area is 4y. So there's more than one root for y that's going to satisfy this equation once you solve for E. I think there will be 3 roots. One will be negative, one will be the depth that you already had, and then the third root that you find is this, the alternate depth that we're looking for. Okay, so hopefully you found that the specific energy under those flow conditions are 1.774 meters. So what we're looking for is there's some other depth besides 0.5 meters. There's some other depth out there that has the same amount of specific energy, and that's the alternate depth. Just to give you a preview into the future, the reason why we're interested in alternate depths is it's related to hydraulic jumps. And so when you've got conditions where the flow conditions can't be sustained in supercritical conditions, it's going to have to jump down to subcritical flow, and it'll go looking for its alternate depth, so the depth that has the same amount of specific energy. So here's what we do. We substitute in that value for E, and then we're solving for the unknown Y. So it comes out to be a cubic equation, and just as an olive branch. Let's try and solve that cubic equation on the Casio. I'll show you. No, I'm trying to be cool about this. All right, so we go, let's see, modes 5, right? Okay, 4 for cubic. All right, so then our equation here was 1, and then minus 1.774. And then 0.31, 86, D. Oh, did I do the wrong thing? Huh? Oh, yeah, okay. So Y was 0, yeah. So we gotta go back over here. 0. Okay. And then this is the one where we say 0.31. 86. Let's see, fingers crossed if this works. There's a negative. Here, this one? Isn't it positive 0.31? All right. All right, so the roots, that's the one I'm looking for, 1.66 meters, because the other roots it's going to tell me are the one I already knew about, the 0.5 meter depth, and then some negative root that I mean, the flow isn't going at negative 3.38 meters. So it's that first root, 1.66. That's the one I'm interested in. So, all right. Those are the roots. So the alternate depth is 1.66 meters. Okay? Everyone feel good about that? You feel really good that since I did it on Casio? You couldn't care less, I know. All right. Critical conditions are when the flow is going at the minimum specific energy. Now, you may be wondering where the equation for the Froude number comes from. Remember, the Froude number, when the Froude number is equal to 1, that is defined as critical conditions. And so Froude number is more than 1 is supercritical. Froude number is less than 1 is subcritical. So consider, here is our equation for specific energy. And if we take the derivative of that, if we say dE dy, then that y just goes to 1, and now we've got dA dy here. And so if you notice that the line, the slope of this at the minimum specific energy, it's straight up and down. So we could, when you're in the subcritical range, you've got a positive slope. When you're in the supercritical range, you've got a negative slope. But the line is straight up and down at the minimum specific energy. And so that's kind of where the Froude number equation comes from, is graphically solving this curve of specific energy. And at critical conditions is when it's going to be straight up. You can solve for the critical depth by changing this equation around and just saying that you've got the critical cross-sectional area, the critical top width, and this equation will always work. It'll always give you the correct critical depth. And just for an example of how to do that, consider the same channel that we've been talking about before, the 4-meter width and the 10 cubic meters per second going through it. We could solve for YC. And let's just take a look at that so that then we can spend the rest of our time on one other thing. So here's finding that critical depth. Okay, so we had the flow rate squared divided by G. The cross-sectional area under critical conditions means that the width is 4, and then it will be some unknown critical depth. And the top width is going to be 4, so we can just substitute in the 4 for that. You can rearrange the equation to solve for YC, and it turns out to be the 0.86 value, that depth that we saw in the spreadsheet table earlier. So you can use this formula under all conditions, but there's actually an easier way than using this formula. If you've got a rectangular channel, then the top width is equal to the bottom width. I've switched over. We're going to say capital B. All right, so you can calculate something called the flow per unit width when you have a rectangular channel. You can't calculate that for other types of channels because the width is changing as a function of depth. But when we had this channel that was 4 meters wide, the rectangular one, and we had a Q of 10 cubic meters per second, lowercase q is capital Q divided by B. And so that's 10 cubic meters per second divided by the channel width of 4 meters. And so what that tells us is that there would be, I think in this case, 2.25 cubic meters per second per meter of width. So basically what you're saying is divide this channel into segments, and you want to know how much flow is going through each one of those segments on average. Now the reality is that more flow would be going through the center part of the channel than through the edges, because the edges are exposed to the frictional contact with the actual channel surface. But we ignore that for now. We just want to know the flow per unit width on an average basis, because you can calculate the critical depth in a really easy way using this formula if you have the flow per unit width. And so let's try that with that abbreviated formula here. We have the, it's 2.5, not 2.25. All right. So the flow per unit width, lowercase q squared divided by g, and that to the third power gives you the same 0.86 meter depth. Now the caution I have to give you is that this only works for a rectangular channel. And so inevitably, this equation will be on the formula sheet for your next exam, and someone will try to use this for like a circular channel or a trapezoidal channel, and it'll just give you the wrong depth. I mean, you'll calculate some YC, but it won't be the correct YC. So you have to know the limitations for this equation. It'll only tell you the critical depth if you can calculate a flow per unit width. And there's no such thing as a flow per unit width for any channel except for a rectangular channel. Okay? All right. All right. This last example we're going to do today is a trapezoidal channel. And we're going to calculate what's the critical slope for this trapezoidal channel. We know the N value. It looks like it's made out of concrete. That N value is associated with concrete. We know the flow rate that's going through it and the side slopes, and the side slopes define the geometry. And we want to find out what slope would induce the critical depth for this trapezoidal channel. So you can see I've given you Manning's equation, and we're going to need to use Manning's equation and the definition of the Froude number is equal to 1 to try and find out what slope would give you the Froude number equal to 1, so critical conditions. So in other words, we want to know what's the critical depth and substitute in the critical depth into Manning's equation and then solve for the slope. All right, I'm going to pause the recording so you can get started on that. Here are all of the geometry parameters that we need for a trapezoidal channel. You can see here that the side slope is 1.5 horizontal to 1 vertical. And so for a trapezoidal channel, the 1 vertical and t is the horizontal component in those formulas here. So here the t is 1.5 and the vertical is 1. So you know the flow rate, and we want to find out the slope that would cause the y sub c depth. Okay.
When you're plugging in the area, it's E plus Ty quantity times Y. So wouldn't it be 3Y plus 3 times 1.5Y?
For the area?
Yeah.
Let's see. Oh, yeah, you may be right about that. Let's see. Area. Yes. Thank you for noticing that. You're right. Yep. So that, right? One more. All right. Thank you. Okay, so it turns out that the critical slope is 0.15%. So that means that any channel that's conveying this much flow, and it has the dimensions of 3 meters wide and the trapezoidal channel with, the 1 to 1.5, any channel that's steeper than that, you're going to have supercritical flow going through the channel. And if the channel slope is less than this, then that would cause subcritical flow. All right, we're out of time. In fact, I've kept you 1 minute late. So I'll pay you back with interest on Thursday with like maybe an extra 15 or 20 seconds, you know? Yeah, I know. On a percentage basis, if you figure the APR of that, it's not bad. So, all right, let me know if you've got questions on the assignment because you've got one due on Thursday. I'll have office hours and I'll be checking my email. So I'll see you then.